Thank you. I'm Lingo from Semilab, and it's my pleasure to take this event and share some recent research data from our company. Okay, my title will be Characterization of High-Performance Solar Cell Materials and Structures, Challenges and Solutions. Okay, by starting this speech, I would like to emphasize that it is very important to detect the tiny cracks, tiny defects, and and measuring parameters precisely is very important. A well-known example is this over the Ohio River, this silver bridge collapsed in 1967 due to only one tiny crack on only one eye-bar of the bridge. Although consequences of defects in PV are not as detrimental, it's still very important. Our mission is to provide measurement solutions following your needs to prevent failures and maintain high yield rate in your PV production. The team working on this task is our company, Semilab, with over 1,600 employees worldwide, and we are developing the equipment for different segments of semiconductor. We have 2 R&D centers for PV, and the one in Budapest as the HQ, the other one in Wuxi, China as a technical center. In this presentation, I will give an insight into our activities to upgrade our metrologies following the actual material and cell processing trends for high-performance silicon solar cell techniques. First, before demonstrating other solutions, I would like to go back to the Silver Bridge collapse analogy, inspired by an analogy. Let me start with the introduction of one of our latest products, which is a seed crystal testing tool. We know tiny cracks and other defects in seed crystal may cause the breakaway of the ingot during the pulling formation. They are unwanted defects. On this purpose, we utilize the IR transmission technology, and we developed such a tool. The challenge from measurement point of view is to get a clear image all through these crystal, and our metrology group in Budapest developed such an advanced optical design to overcome this challenge. See, with this design, we can get clear image all through this seed crystal. Not only the body part, but also the neck part is very clear. Let's move to a rapid visualization of measurement techniques for the entire PV production chain. I highlighted and I will present the seed crystal testing, resistivity, and lifetime measurements for ingot manufacturing, where our company made significant developments in this year. We know due to the excellent surface passivation conditions achievable in BC cell architectures, further reducing the recombination rate in the wafer enables to achieve very high efficiency. However, in mass production, it is this requires to reduce the doping concentration, say, to increase the resistivity. As it is highlighted in the Taiyang news report, the wafers with around 20 ohm centimeters are already applied. And it is expectable the even higher, like 40, 60, 80 will be pop up in the very soon. However, in this range, the cell performance gets very sensitive to the variation in doping concentration. Therefore, we need precise control. Eddy current is one of the most widely used technique in this inline measurement, inline resistivity measurement, but its application in this high resistivity range is challenging due to the lower signal and the higher influence of the environmental condition. Our engineer this year optimized the probe parameters from 0.5 to 100 ohm centimeter. It maintained high linearity, I mean the excellent correlation with reference for PP within plus minus 3% accuracy. And it still has good repeatability even above 100 ohm centimeters. Another kind of new type of sensor is developed and already tested. It extends the measurement range up to 1,000 ohm centimeter and will be commercially available in the next year. The other important electrical parameter to control the quality of the ingot is the carrier lifetime. Several years ago, we introduced the upgraded version of our laser-based eddy current PCD sensor, which enabled the measurement of bulk lifetime in pure transient mode, evaluating the entire carrier lifetime range within 1 to 2 seconds automatically. And as shown in this example, it provides accurately and reliable single lifetime value at certain injection level. However, for better characterization, not only the carrier lifetime, but its dependence on injection level is relevant as well. Due to interplay of several physical phenomena, it is challenging to obtain on thick materials. Therefore, our scientists in Budapest developed a complex iterative simulation-based algorithm to provide this information. The model needs a couple of physical phenomena, like I listed here: a carrier, absorption, diffusion, the bulk, and surface recombination, blah, blah. It makes the proper evaluation very challenging. However, we did it, and we first applied this unique iterative evaluation technique on different P-type ingots from an RCZ pooling sequence. It is shown the results indicate convincing agreement to values obtained on neighboring wafers with symmetric amorphous silicon passivation. When moving to N-type wafers, we investigate it on the 1.5 centimeter thick slugs, as it is used in the industry qualification. When we were doing this, we faced an interesting challenge. The 1.6 sample, 1.5 centimeter thick sample is not thick enough. It started behaving as a wafer during the measurement because the impact of the surface recombination gets stronger. And it resulted in that carrier lifetime was limited by the carrier diffusion processes at low injection levels. The good thing is that this contribution of surface recombination can be corrected precisely. So bulk lifetime can be determined accurately. At the same time, our simulation also provided the same result at low injection levels. This indicates the reliability of our model. Here are some more data with bulk carrier lifetime above 20 milliseconds. It indicates that our carrier lifetime metrology is applicable for modern silicon materials, and we will be happy to measure some ingots with even longer carrier lifetime. Our carrier lifetime measurement is not only accurate, but very easy to integrate into automated production lines, where it provides the same excellent performance and experience with manual use. Okay, other challenging task is to perform precise and rapid measurements during cell production, for which SEMLab offers several solutions to measure the layer thickness, carrier lifetime, defects in the samples, and the sheet resistance of diffused implanted layer, polysilicon layers. I'll provide more insights into the novel solutions for carrier lifetime and sheet resistance measurements. Moving to the measurement solution for cell manufacturing, let me start with carrier lifetime again. Since injection-dependent measurements on lifetime samples enable to predict IV parameter of the finished cell. However, in standard routine, the PCD measurements require the calibration of a sensor, the accurate value of sheet resistance of polysilicon, or any other conducting layers. And you need to rely on literature data for injection and temperature-dependent mobility models. Therefore, our scientists developed a very clear way. You see, we provide a general solution for all these factors. Using laser means that we can play with output power. So we here giving the output power by step with different intensity accurately, and meanwhile we collect the eddy signal, which reference the conductivity of the sample. With these data, we can comparing the steady state and the decay dynamics at several different signal level. It enables to construct the self-calibration of the sensor signal I mentioned earlier, and to injection level without using mobility models and not rely on sheet resistance or doping data. On the other hand, if we already know some of these factor parameters, we can determine the rest based on the evaluation model. In the next page, we prove the accuracy of our model using the mobility data. We confirm the accuracy of this model by calculating the mobility of excess carrier using this method. Results on these symmetric amorphous silicon passivated wafers agrees very well to literature data and aligned also very well to our previous results using a more complex and time-consuming method to measure the data. I would like to mention that a single carrier lifetime like this takes only less than 1 second. This is a prototype of our laser PCD lifetime measurement system equipped with the mentioned new evaluation model. It is designed for inline and will be commercially ready in 2026. This page is about the sheet resistance. We know and we have already applied these non-contact techniques, the JPV method in PERC and the HAT cell structures. But what about the doped polysilicon layers in TOPCon and BC cells? Our recent researches prove that the two methods correlate pretty well in the case of P plus poly layers on N-type wafers, say on emitter-type junction. In this case, the space charge region below the polysilicon layer isolates the polysilicon layer from the substrate. So both measurements, meaning the contacting 4pp way and the non-contacting JPV method, both methods are sensitive enough to only the top layer, whose sheet resistance is our interest. In contrast, if we take the measurements on the N plus polysilicon, the current flow in both the N-type substrate and in the polysilicon layer. However, while for JPV measurements, electrons are crossing the tunnel oxide only from inside the substrate. Due to the substrate has low resistance, this is a selective junction. For 4pp measurements, the current is injected externally and it needs to pass the tunnel oxide in both directions. Since it needs to pass in the reverse direction with high resistance as well, the measurement will be more sensitive to the properties of the tunnel oxide layer. This is reflected in the results. Big difference between the two methods and the large sensitivity to actual tunnel oxide property with 4pp measurements. So practically we can say 4pp measurements are able to sort of characterize the quality of the tunnel oxide layer as well while measuring the sheet resistance. Therefore, for inline processing control, we would like to offer 4pp for N plus layers measurement because it's practically more sensitive, and offer JPV, the non-contacting way, for P plus polylayer because it's more flexible and reliable enough. Last, I would like to mention that we released a desktop tool this year. It is basically a sheet resistance measurement tool, but suitable to integrate 3 different methods: 4pp, JPV, and eddy current. It can be used on multiple sample types, and it is most versatile sheet resistance characterization tool on the market. Okay. Here's my report. Thank you, everyone. Thank you for listening.